Good evening. Let me add my welcome to Hassan's to the Royal Institution. I'm Tim Bestwick. I'm from the UK's Atomic Energy Authority, and we're the UK organisation that is developing fusion. So fusion has been in the news recently. It has an increasing media presence. For a long time it was really a research topic, but really now it's becoming much more prominent. And we thought, together with Royal Institution, it was a good opportunity now to look beyond those headlines, dig a little bit into it and ask some of the questions and go in a bit further behind what we read in the headlines in the media. So we've put together a series of 3 lectures, and this is the first one tonight. And tonight we're going to concentrate on 2 questions. Really, broadly speaking, it's why do we need fusion? An important question, I think. And the second one is, broadly, why is it so difficult? And that last one we're going to split into 2. There's the difficulty and the challenges of the plasma, and then harnessing that to do what we need to produce energy. So the word expert is often thrown around a bit loosely, perhaps, but tonight we have 3 speakers who genuinely are true experts and thought leaders in their fields. And I'm delighted that to take us through those aspects of fusion, we have Mark Maslin, Dennis Whyte, and Jenny Kane, who are going to talk to us about those questions. Why do we need fusion, and why is it so difficult? And first up, we have Mark.
Thank you very much, Tim. So I'm literally the opening act. I'm here to try to persuade you that fusion is critical because of the state of the planet. I love this cartoon. We all suffered under COVID. We all had our lives restricted, and we were all worried about flattening the curve. But what was really interesting was while we were all closeted and we were stuck, we realized that climate change was a bigger threat that was coming down the future. And so it's really quite apt that we're here. So we go back 150 years. Eunice Foote, an American female scientist and activist, she discovered the greenhouse effect. Very simple. She took 2 test tubes, one filled with air, one filled with CO2. She put thermometers in them and left them out in the sun and recorded. The one with CO2 got hotter quicker, got to a higher temperature, and lost the heat slower than the one with air. And the next year, she published it, and it was presented at a conference by her male colleague. But things have moved on now, okay, as you will see from today. And then John Tyndall, 5 years later, here, in the Royal Institution, used this equipment, which is somewhere in the dusty basements here, I can assure you, and used a thermocouple to show how much heat each gas absorbed. And he realized that water vapor was the most important greenhouse gas, followed by carbon dioxide, methane. So, we know about the greenhouse effect 150 years ago. But what is climate change? Because we hear it bandied around in the media a lot, and we also hear lots of people going, oh, it's nothing to worry about. Well, if you think about it, the sun's energy, which does come from fusion, see, there's the link, okay, comes from fusion. This energy is mainly in the light, okay? It's shortwave radiation, and it hits the Earth. About 1/3 of it bounces straight back into space, off white clouds, off ice sheets, because of that reflective albedo. 2/3 hits the Earth. Now, just imagine you're not here. You're on a tropical beach. Just imagine. You've got your favorite cocktail, mine's a mojito, and what happens? You feel hot. That's because the light energy is hitting your skin and it's converting to heat, and you're radiating that radiate that heat away from you. The Earth does exactly the same. And it gives that heat up to the atmosphere, and this is where the magic of the greenhouse gases come in. Water vapor, methane, and CO2. They absorb some of that heat, they hold on to it, and they keep the world nice and warm. Strip out those greenhouse gases, and the temperature of the Earth would drop by about 35 degrees. So let's be generous. So that would be an English winter of, say, minus 15, and an English summer of minus 15, and an English winter of about minus 35. Okay, so greenhouse gases are good, except in 1938, okay, this is not suddenly discovered in the 80s. It's 1938, and Guy Callender shows with temperature data from around the world and some CO2 data that have been measured that temperatures were already rising. And he worked for the British Coal Board, so he knew burning coal produced CO2, and he was the first person to talk about global warming, and it was already happening. Yeah, we sort of ignored it from then. So CO2, this is the classic Keeling curve. We have now made CO2 in the atmosphere 50% higher than it was during pre-industrial times. Methane is 150% higher than it was before the Industrial Revolution. And I can tell you as a paleoclimatologist, it's been the highest time, it's been about the same as about 3 million years ago. So we're pushing the atmosphere out of its normal alignment. And there you are, Keeling curve going up every single year. Now, this is where a little bit of audience participation, be honest, because the cameras are facing me, not you, so you're fine. How many of you actually like skiing and snowboarding? Yes. Okay, memo, you need to do it really quickly, okay? So the top left graph, guess what? Northern Hemisphere snow cover has been dropping every single year since the 1960s. If we look at sea ice extent in the Arctic, it's been reducing. We also have probably the smallest amount of sea ice in the Antarctic we've ever recorded this year. And the one that really worries me, and this is very esoteric and very geeky, is the heat content of the upper ocean. So that's the top 1,000 meters. Remember, the oceans cover 70% of the Earth, and it's just absorbing heat. And we know it has a high inertia, and therefore there's a lot of energy being stored there. And the slow creep of sea level, which is never going to catch us unawares, but is rising at about 8 to 9 millimeters per year. It's already risen by about 24 centimeters. So that's the evidence that climate change has already happened. And of course, air temperatures. Highly variable, but as you can see, strong warming through the last 100 years. And 2020 was the warmest year on record. Yeah, and I'm going to put a bet down, which I know I'm going to win. 2023 will be warmer, and probably by quite a lot. I'm also presenting now graphs. I know all of you are here to see wonderful physics graphs, but graphs are not for everybody. So Ed Hawkins from Reading University beautifully put the climate stripes, or the warming stripes. And so this is what they look like for England since the 1850s. Blue, cold, red, warm. But this has also become a bit of a cottage industry. So you can have a tie, okay? And the thing is, sometimes I give this same talk to CEOs and big companies. And so I say, look, if you can afford a Tesla, you can afford to wrap it properly, show your true stripes, okay? T-shirt, I can afford the T-shirt. I'm not going to wear the leggings, okay? That really would put you off. And of course, the face mask that luckily we now don't have to wear all the time. So, let's be serious about the events that have happened. So for me, last year was a seminal moment. We had a 40-degree heat wave in London. The peak temperature for July for the last decade is 24 degrees. This was 16 degrees warmer than it should have been, and 3,000 excess deaths occurred in those 2 days because of that heat. And look what's happened to 2023, one of the warmest, actually the warmest summer we've ever recorded. And you've seen all the extreme events. Now, this is on the NOAA website. The floods in Pakistan, 30 million people affected. The heat waves in North America, in Southern Europe, and in China. We've seen them happening more and more. So, what about the future? Okay, I'm a scientist, so I'd like to have lots of little Earths. I'd like to double CO2, half CO2, bit like the physicists, they actually get to play, whereas we've only got one, and we're sort of doing a really massive experiment on it anyway, so I'm not allowed to play anymore. So, how do we do it? Supercomputers. So we have gridded networks around the Earth, which basically go into the Earth, go into the ocean, vegetation, into the atmosphere. We have cloud models, we have the chemistry, and on the, right-hand side, this is the increase in computer models. So the first models that were produced for the 1990 report of the IPCC, as you can see, bit of a joke here, guess what? Europe really was part of Britain. So yeah, no Brexit then. As you can see now, unfortunately, we have much higher resolution models down to sort of like 100 or sometimes 50 kilometers, and we have this fantastic revolution. Now, the reason being is because of, guess what? Computer power. Computer power has gone exponential. But the really interesting thing is the story is exactly the same. You take the world, you put greenhouse gases into the atmosphere, it warms up, it causes climate change. So the science has got more and more detail, we have more and more knowledge, and guess what? It's exactly the same as we knew in 1990. Right, so what does the future look like? Because again, guess what? The physics is really good, the chemistry is really good, the science is really good. Guess what the problem is? Yeah, you lot. And by you lot, I don't mean the people in this audience, I mean all the 8 billion of us, okay? How many are there going to be by 2050? How are we going to generate our energy? How are we going to make our food? And so therefore, with economists and social scientists, we create scenarios, which is a polite way of going future stories. And so the red one is we had no climate policies. This is something I was talking to people about 10 years ago. We're looking at 4 to 5.5 degrees warming. That's not going to happen. Current policies, 3.1 to 3.7 degrees. And if all the pledges made at COP26 and the other climate meetings are fulfilled, 2.4 to 2.8. That's still nowhere near the 2-degree one that we promised, the leaders of the world promised in Paris in 2015. And it's certainly nowhere near the 1.5. Remember, we're at 1.2 already. So, what are the effects of climate change? Just to really upset you, and then I'll move on to solutions. More extreme storms, floods, droughts, heat waves, and wildfires. We've seen those, which may lead to food and water insecurity. But I'm going to talk about that. We make enough food to feed 10 billion people, but there are still hungry people in the world. May lead to migration and conflict. Well, possibly. But if you look around the world at conflicts, they're not because of environmental problems, they're because of politics. May lead to tipping points. So just to actually put some tipping points up, there are major areas of the world that when we go above 1.5 degrees, and definitely above 2 degrees, scientists that I trust believe that there are points where the Amazon will start to die off. The Arctic ice will move and melt. We will lose parts of Greenland and Western Antarctic ice sheet. We haven't got there yet. We don't think. So, Paris Agreement, and this is where I have to say, yeah, as an Englishman, I have to say, oh, the French were magnificent. Okay, whenever I say that, that stresses me. But they were brilliant. They got the whole world to agree to keep climate change to 2 degrees and, if possible, 1.5 degrees. And in their statement, they said, well, achieving this will require the complete transformation of energy generation, okay, industry, infrastructure, and personal behaviors. Okay, guys? So you're one of the 4 bits. And this is the reason why. The red line is the increase in emissions up until last year. It doesn't have last year because 2022 was the most greenhouse gases we ever pumped into the atmosphere in a year. So no, we haven't flattened the curve. We haven't even stopped the rise. Now, if we want to keep to 1.5 degrees, we need to get to net zero by 2050. Okay? So that means Nobody emits anything, or if they do, they have a mechanism for sucking out, like growing forests or direct air capture. And then this is the bit where I'm a little bit quiet, because what we don't tell you is once we get there, which will be an amazing achievement, well done, we have to suck CO2 out of the atmosphere for the next 50 years to keep it at 1.5 degrees, but I'm not going to tell you that because it's really bad anyway. Right, moving on. So, where are we with this? So, 80% of the world's energy now is produced by fossil fuels. 80%. Now, but you all know that renewables are going mad. We've got exponential growth in solar, in wind, in electric vehicles. 26% of all cars sold in China last year were electric. Batteries, exponential. But all that is doing is eating up the increased demand in energy that the world has every single year. Simon Sharp's book, brilliant book, basically summarizes in 250 pages. I can summarize it. He says, we're doing brilliantly, but we have to do everything 5 times faster. 5 times faster, okay? But this is interesting because what it means is by 2050, we have to get rid of that 80% of fossil fuel. And guess what? We need renewables. We also need to think about how we actually increase energy. There's a huge population that doesn't have enough energy, and there's a huge population that has too much energy and producing lots of CO2. This is the energy poverty and CO2 emission curve. And think, at the state of the world now, 7 million children die needlessly every year because of preventable diseases and starvation. That's the population of Greater London. 825 million people go to bed feeling hungry every night. That's gone up by 25 million for the first time in the last 5 years. In a world where we produce enough food for 10 billion people. 1 billion people have no access to clean, safe drinking water, and 1.1 billion, that's 1 in 8 people, do not have access to electricity, which is madness. We have all of the ability to make that, and make it without CO2. I'm also going to point out that actually, if we look at emissions, the top richest 10%, and by the way, all of you, unless you're a student, all of you, okay, are part of that 10%, produce 50% of the lifestyle emissions going into the atmosphere. So this is a rich person's problem that we need to deal with at this moment in time. And I'm going to leave you with this one thought, and this is why fusion is absolutely essential. The most conservative estimate for energy growth by 2050 is that we need to double it. Others, who are very respected, like McKinsey, suggest it might triple. So think about it. Today, we have to produce 80% of the energy for the whole world as renewables. By 2050, we have to produce 180% of energy as renewables, or even 280% of energy. Think about that. That's the first thing, the scale. The second thing is, when I actually said this at the Fusion 2022 conference here in the Science Museum last year, I also turned around to them and went, and just think how much money that is worth. If you can produce 280% of the world's energy from fusion. So, it's not just a science. We really do need fusion to make up the gap between what renewables can do and what we need to actually lift everybody out of energy poverty, and make sure that we have a clean world and we stay below that 1.5 degrees. Thank you very much. I'm now going to pass over to Dennis, who's going to tell us how we're going to do it.
Oh, yeah, no pressure. Thank you for that. It is really important to understand this context, and in a sense, my comment to this is like you're going to see that fusion is not easy, but this is why we need to try it. So the slides coming up. There we go. Okay. So the answer is actually in front of us because life in the universe and you are possible because of fusion, because it's the process that powers stars. And stars and our own sun, essentially conversion engines that take hydrogen, the most abundant element in the universe, and convert it into helium. So on Earth, the idea is we actually take heavy forms of hydrogen, these ones, we fuse them together, like happens in the center, so this means we jam them together. And on the other side of this, we remake the elements that were originally there. It turns out the things on the right have less mass than the things on the left. Where does that mass go? It goes into energy by E equals mc squared, an equation you might have heard of before. So what does this mean? This releases enormous amounts of energy, and it can become a terrestrial source of energy with an effectively inexhaustible fuel source. It's intrinsically safe, and it has high power density, which are the features of what we see were required as well too. Let's walk through this. Where does this come from? So it's not a typical energy source of how you're thinking of hydrogen or carbon-based fuels, which come from chemical reactions. This comes from the rearrangement of the nuclei themselves. It is what makes the element its own identity. So just a brief recollection, the nucleus, which makes up an incredibly small fraction, but almost all the mass of the atom, is made up of protons and neutrons, and it's surrounded by electrons. Chemical reactions come from rearranging electron orbits. These sources come from this famous curve, which is the thing that's on the right-hand side, which tells us that we know this, that in fact, because of Rutherford, who discovered the nucleus, is that if you look at the masses and therefore the energy stability of all of the existing isotopes, this makes this very famous curve. And what this shows you is that the most stable element is iron. So anything that's on the right and goes up this curve releases energy by E equals mc squared. And that's fission, which is on the right, because you take the heaviest, most unstable nuclei and split them apart, and that makes fission. And because it goes up the curve, it releases energy. This is traditional nuclear energy. Fusion is literally the opposite process. What it does is it takes the lightest elements, which are on the left-hand side of the curve, and boosts them up. So what does this mean numerically? It's really important to look at numbers. So if you take a look at the energy per mass of this, is that chemical reactions I'll just use this unit conveniently, I'll just make that 1. And if you look at fusion, you get something like 5 million times the energy per mass of that. And fission is around 1/5 of this. This comes from the fundamental fact that you're changing much larger mass, and therefore the energy is released. The way that we know this, by the way, is that this is why the sun is going to last for about 10 billion years. It has a very hard time converting all the fuel because of how much energy is released. Then what's the other part? Well, the threshold temperature, how do you get it to burn, is that, we're familiar with this with fire. Fusion has a requirement of 50 million degrees on Earth. What? Okay. Fission is easy because it has 0 temperature requirement. But the fundamentals of this is that what comes out of the product, and what comes out of the burn of chemicals is the thing that we were just discussing, which is CO. This has to come from it. You can't avoid it. And what comes out of fission is a wide array of radioactive isotopes because it comes from the process. And what comes out of fusion is helium, an inert gas, and a free neutron. So I'm going to explain this in a way that it deals with essentially recycling. We all like recycling. Fusion works on recycling. And what I mean by this is that fusion energy sustains itself by recycling its own heat and also by recycling neutrons, which are this fundamental aspect of it. So how does it all start off? So this is the basic process. So we take these two ones on the left, deuterium and tritium, you see them over here, and they have, we'll just start there. They have an average energy, this is in millions of units of those energies that I said were chemical energy. This is a staggering energy and temperature, because even at 0.01, that translates into Celsius at 100 million degrees Celsius. And when you get to that condition, the average energy of the particles is high enough that they can get close enough to fuse together and change into what's on the right, which is helium and this free neutron. And the amount of energy is way, way bigger on the right-hand side of this than on the left because of E equals mc squared. So this tells us why fusion is hard right away, and it's actually what stars are made of. It's called the plasma state because it's very, very hot, and it's at 100 million degrees. So at this point, you're about ready to go home, and what is it? There's the Rugby World Cup going on, and you're ready to go watch that. And you're saying, wait, you can actually make something 100 million degrees? Yes. So this is from the laboratory experiment at MIT. In fact, there's a picture of the one that's not too far from here, or just behind me as well too. Yes, we have routinely achieved 100 million degrees on the planet Earth. And how this is done is that we actually use a containment system which has a very powerful magnetic field, which basically allows us to suspend the star in place without actually touching a physical object. And it uses a magnetic field that is around 1 million times the Earth's magnetic field. So this is also telling you, it's like, oh yeah, this is hard technology, but in fact, it is in fact feasible and is done in many experiments around the world. So how does the rest of it, so imagine that you get to 100 million degrees, what do you actually use this for? Well, a very key point in this is that the energy that comes out of this is that a distinguishing feature of plasmas is that they're made of particles that have electric charge. And what this means is that the thing on the right, which has electric charges, gets contained by the same mechanism. So this helium has extraordinarily high energy, and because it has charged particles interacting with other charged particles on the left, it essentially forces that energy to be recycled as heat back into that. So this is the way that, in fact, the fusion fuel, the plasma, keeps itself hot through its own fusion reactions. We instinctively know this is true because tell me what power source the sun is plugged into. It isn't plugged into anything because it keeps itself hot and therefore enables all the remaining fusion reactions. Wait, we can actually get net energy from fusion? Yes. What's cool about this slide, I couldn't show this slide a year ago. This was, so this is the National Ignition Facility at Lawrence, at a laboratory in the United States in California. And in this amazing facility, what they did is they had 2 units of this energy, of laser energy, and they got 3 units of energy from the fusion that came out of this. And it's complex technology, which I will not go through. The important aspect of the science of this was they got to the place where that product, that helium particle that is the product of the fusion, was the dominant heating source inside of the fuel. It was a star instantaneously on Earth. So that's pretty good for a group of, for some, from primates, running around. We actually figured out how to make a star on the planet Earth. That's pretty aspiring. And by the way, this feature is, so regardless of the technology that was used to get there, this is a common science feature to every energy source. You basically have to make the star light up. And then what's the last part? Well, you basically need to keep it going. So what happens? Well, most of the energy is actually in this particle that has no electric charge called the neutron, and it is going very, very fast. So this is good in a way because it escapes any containment. And what you have to do then, but it contains 80% of the energy. So you throw something in front of this. So it's not 100 million degrees anymore. You throw an object like a glass, like water, or it's probably not going to be water, but anything that's in the solid or liquid phase. And what happens is this particle is forced to basically give up its energy through collisions into heat. And what's the important part of this is that what does fusion produce on Earth? It actually produces heat. It's not an electricity source, it's a heat source. So it goes to the other comment, which was there as well too. One of the challenges of the energy transition is not that we make electricity, just electricity. We have to replace all of our energy sources and energy uses, not just those which make electricity. And then finally, we put lithium in front of this because there's another reaction that occurs, because tritium doesn't actually exist naturally on Earth. So we use this free neutron as a kind of catalyst, because this greatly increases the amount of fusion power that you can make in a given system. This produces another helium particle and another one of these tritium particles. It's not magic, we actually do this. And in the end, what this means is that what goes into a power plant of fusion is deuterium and lithium, and these don't come out again. These are the consumables. And what you get out are 2 helium particles. And this neutron is actually recycled, as I said, like a catalyst almost inside of it. And the actual ash particle of the fuel cycle itself is helium, which is an inert, harmless gas. And you say, wait, we can change elements like alchemy? Yes, we do this. In fact, I'm just showing this one parochially because I'm proud of my students. This was done by a set of MIT students 2 weeks ago. They were sending these high-energy neutrons into a special molten salt, made it collide with lithium, and they were measuring the tritium that was made in this as well, too. So yes, we are kind of the alchemists of the modern era, I guess we would call ourselves. Hey, wow, you're painting such a rosy picture, Dennis. What's waiting in front of us? Well, these neutrons are very, very intriguing. In fact, you'll hear more about this from the next speaker, is that they're so energetic that they can literally remake the elements inside any of the material that's surrounding them. And this is required because you have to capture the heat. These have to be inside complex vacuum systems. In the end, we'll see more about this. In the end, what we lack is the complex and integrated and reliable solutions that would make fusion an economic energy source. Most of the science is actually, we've grabbed this and actually demonstrated it. So the science of fusion energy, this is really important because even though it's difficult, it drives the need for this. There are no polluting emissions because you're making helium, certainly no carbon. You have a freely available and inexhaustible fuel supply. Why is this? It's because the fuel comes basically from water. And this is not, and you're getting 5 to 20 million times the amount of energy than you would get from a chemical reaction. You basically cannot run out of the fuel, okay? You get flexible generation everywhere and anywhere because you can turn it on when you want. Meltdowns are not possible because of the fact that it's making helium which can no longer fuse. So in the end, you know that you can actually make energy at civilization scale. So how does this all work? The reason it works in stars is that the thing that we think of as hot at the surface of the sun, which is at around 5,000 degrees Celsius, the center of our sun is at around 20 million degrees Celsius. And that's where the fusion is occurring. So how does this all hang together? If something's getting really hot in the middle, why doesn't it just escape into outer space and then cool off? Because it can't, because it's held in place by the gravity of the sun itself. And this is why, and gravity is an extremely weak force, fundamental force. So in the end, this is why stars are incredibly large. They're not small by default. So we have to overcome that and use a much more powerful force, which is essentially the electromagnetic force, which is many orders of magnitude higher. And the idea is we basically exert a force on these particles, which are made up of the fuel, and this means that then we can shrink down the size of the star to something that we can fit on Earth into a power plant. So how does this all work? Because it all sounds confused. How do you hold something at 100 million degrees? You can't. What will happen is it will just get cold, no fusion will happen, or you would melt the interior of this thing. So we're actually not using a physical object. The purpose of that magnetic field is what we use are electromagnets, which are probably demonstrated right here around this desk or something like this, because understood by Faraday and Ampere, that what you do in an electromagnet is you pass an electric current through a wire and put it in a pattern. This will make a strong magnetic field. And these electromagnets make the magnetic field, but the electromagnets have no idea there's a fusion fuel inside of them. And the fusion fuel actually has no idea that there are electromagnets outside of them. So it's a force which is exerted at a distance, and this allows you to hold it without physically touching it. So why do we care about this? Well, so this plasma is the state of matter when things get hot. And we're not very familiar, we don't teach this very well in school, by the way, because about 99% of the universe is in the plasma state, because that's what all stars are. So above 5,000 degrees, that's this, because fusion happens at 50 million degrees and above, everything's in the plasma state. So the reason that we study plasmas, it's the equivalent of knowing a steam table and being able to build a locomotive back in the old days, right? And it also behaves very differently because its behavior is set by the fact that it interacts through the charges of the particles rather than just physically knocking into them as well, too. So what are all the conditions necessary to do this? It's like building a fire in the end. What is required, and we all understand building a fire because this relies on recycling its heat rather than particles. You have density of wood, they have the temperature, and then you put it into a configuration so that one log keeps the other logs hot as well too. It's the same in fusion. Except the extraordinary condition is the middle one, that the temperature is at around 100 million degrees Celsius. But in the primary way that we're considering doing magnetic fusion, the density of the particles is extremely tenuous, 100,000 times less dense than air, and you only have to hold it in place for 1 second, voila, you've got fusion. Now, here's some equations, which I'm not going to explain. But in the end, actually, it comes down to the same thing. It's the density of the fuel, it's the temperature, and it's how long you can contain the energy. So I have to show this plot because it was actually derived by a British scientist in the 1950s, John Lawson, who must have been at the UKAEA at that time, or its predecessor, and realized this basically set the conditions for making the star on Earth. The key thing to look at this is on the horizontal axis is the temperature. So 10, which is 10 to the 1, which you see on there, that is 100 million degrees Celsius. And then these configurations it turns out it's the product of the density of the fuel and the confinement time. You hit these with any configuration, you will start making net energy out of this system. So I'm not going to show you these equations. Instead, I'm going to point out a few interesting aspects of this. So the temperature is extremely high, but if you go to magnetic fusion and the densities that we have, I say this has a density of 100,000 times less dense than air. So what this means is that the energy density of the fuel is less than boiling water. It's a lot less than boiling water. This is also why fusion is intrinsically safe. It's because you think, what happens if this escapes? Will it turn everything to 100 million degrees? Nothing happens because it just turns back to room temperature. And then a really key one is because the fusion reactions are controlled by heating, not a chain reaction. It's physically impossible for the process to run away. You can't actually create a meltdown, even if you tried, because it's physically impossible. And in the end, the reason that we tried deuterium fusion, that you can see by this plot, where these are factors of 10, by the way, on there, it's at least a factor of 10 easier, in fact, than any of the other fuel sources. So you say, well, wait, so you've drawn this theoretical curve. Wait, we've actually figured out how to put the fusion fire together and make net energy? Yes, mostly. And what I mean by this is one of the extraordinary, and in the popular press, or maybe your conception, is that fusion was an endeavor that has failed. Far, far from it. If you look at this, this is amazing to think over here again. And these are factors of 10, by the way. You start with some of the very earliest experiments. In fact, I see Zeta there, which is in fact a British experiment as well too. One's in the US, one's around the world. We went up this and we improved the performance of this both in temperature, getting up to 10, which is 100 million degrees, and towards these curves on the upper right, which is where you start getting net energy out of the system. Those are real data points. Yes, we have made temperatures in excess of 100 million degrees on the planet Earth. And you can see about how we filled that out. We got right to the edge, in fact, of me starting to make net energy out of the system. That's, in fact, the next frontier, because now the key thing to make an economic and reliable energy source, you must have a large ratio of fusion power out compared to the energy that you have to put into it. And we are right at the verge, in fact, of that. So I'll conclude with this because I hope I convinced you that this isn't science fiction. I mean, it's amazing science, but it's not science fiction. And really what we have in front of us, if you put all those together, my look at this as, because of the compelling needs of climate change and the timescales, we have both challenges and opportunities of commercial fusion. Because we can do this in the lab for a long time, but until we build units that actually get out and power the world, this is not going to make a difference. And it has many amazing things. You get low marginal costs because the fuel is free. So you get firm and rampable generation, which is unlike what you get actually with renewables. It's scalable because we should be able to build it anywhere. And we can also leverage existing infrastructure, which is what do I mean by that? Energy delivery, because it makes heat. And almost everything we use in the energy system uses heat already. So we can just replace the interior of that with a fusion device. We can get there inherently safe, as I pointed out. Our challenges are really about making it economically competitive so that we get a high quality of heat at a low cost per unit of energy. And then finally, what does it look like? It looks like all the other hard tech innovations that the human species has taken on. It takes more than science. It takes integrated technology. It takes innovations in fact, how you finance it. It takes innovations in the kind of organizations that you build to do these things. But we've done it because you already showed it. Like, you look at this. Like, the transistor was invented, in the late 1950s, and we turned it into this. It's like, that's the challenge in front of us, because we need to keep making those innovations to make fusion a practical and reliable and economic energy source. And that's the topic of our next speaker. So please welcome Jenny in.
Hello. Just wait for my slides to come up. So I am taking you from fusion experiments to fusion power plant. So I am Jenny Kane, and I am the lead for the team that is designing and delivering the vacuum vessel for the STEP prototype power plant. STEP is a government initiative program where we are designing and we will be building a prototype power plant that will produce net electricity to the grid and its own fuel right here in the UK in Nottinghamshire in West Burton. So I am very much in the business of making power plants, fusion power plants. STEP stands for spherical tokamak for energy production. So from that, you get the idea. I'm also into magnetic confinement fusion, so tokamaks. So we've been left from Dennis's talk with a lot of very high kinetic energy neutrons. You can see them all here in the red, smashing into the walls of our tokamak device, into the center of our power plant. But what we need to do is we need to convert those neutrons into the heat we want to either go out directly to factories or to make hydrogen, or convert it into electricity. How do we do that? Well, we do it in a power plant. But the power plant will look incredibly similar, as Dennis said, to an oil or a gas or a fission power plant. All we're doing is changing the kettle in the middle, the bit that makes the heat. And so all we do is we add into the middle our fusion tokamak. But how do we make it commercially viable? Well, first of all, we better produce some electricity out, So we'll talk a bit about that. We then, as Dennis mentioned, we need to produce that tritium fuel. And most importantly, of course, it needs to be at a price in the end that we can all afford, that the world can afford. And that means it needs to have the availability that we need, and it needs to be fast to maintain. Now, we need to take those first big steps to net energy production and fuel self-sufficiency, and on the way, start getting an idea of how maintainability and availability will work. So let's home in now on that kettle, onto the tokamak. This is a preconceptual design of the STEP tokamak. So you've got those magnets around there, they're driving the plasma and they're containing the plasma. We then get to the bits I'm really interested in, because we've got the vacuum vessel. We need to be working with a vacuum inside that plasma chamber to make the fusion happen. There's the exhaust to get that helium gas ash out. And we also, in a spherical tokamak, have a very narrow center column. It's about 3 meters in diameter-ish on a spherical tokamak of this kind of scale. And we've got to shield those magnets, because those magnets do not like radiation. And what are we doing? We're pumping out neutrons. So I'm going to touch a little bit on that. But mainly, what I'm going to talk about is this bit. Because all the other things I just showed, they already exist in fusion experiments all around the world. We already have all those parts of the fusion power plant, but we don't yet have the blankets. Now, blankets are incredibly important because they are the bit that convert a fusion experimental machine to a fusion power plant. They are the bit that wrap around, that's why they're called a blanket, they wrap around the plasma and the neutrons crash into them. We have some kind of a coolant, it could be a liquid, it could be gas, that those neutrons go into, and they convert the kinetic energy into the heat energy that then goes off to the turbines or directly out to the industry or your homes, and it either gets converted to electricity or we use it as heat. They also need to breed the tritium that we need. As we said, tritium is not naturally abundant, doesn't naturally occur on Earth, and at the moment we have kind of tens of kilograms of tritium in the world. That's fine, because our experimental reactors, they only use grams of tritium. But once we get to power plants, we're kind of in the hundreds of kilograms kind of place. But that's okay, because we can generate it ourselves. Because of that lovely situation that you have high-energy neutrons that go into lithium and you can produce tritium, we can breed our own tritium, our own fuel. We also need to survive that plasma. So the blanket also must survive the plasma, more about that in a second, and then that shielding aspect to stop those magnets on the outside becoming damaged. So there you can see a nice schematic of our blanket. You've got your neutrons coming in, very high temperature, very high heat loads, into your first wall, into your breeding zone where you're going to make your tritium, and your thermal extraction zone into the shields, and then you're protecting those magnets. Let's take each of them in turn. Survival, first of all. So what I've done is I've overlaid a radiative heat flux map onto our plasma. And what you can see there is you're getting 1 megawatt per meter squared steady state on that first wall. That is equivalent to a jet engine or inside an internal combustion engine piston area. And so you need to do something pretty fancy to make sure that you get that heat away and you aren't going to destroy your first wall. You put something pretty strong and hard on the front, something like tungsten, or maybe it's a carbon or beryllium, and then you must be actively cooled. So you need to get from that tungsten to something that is very highly thermally conductive and into a pipe or a channel where you're shooting through fluids, it could be a liquid, it could be a gas, to take away that heat. Very similar to a jet turbine engine, and indeed we can use a lot of that technology in what we do in fusion. So you've got through your first wall, which, by the way, is only a few centimetres at the most thick. And don't forget, it must let the neutrons go through because it's got to get to the blanket, because it's the blanket where you're going to make the heat generation, and you need to breathe that tritium. So let's talk about generating heat. So you've got a Sankey diagram, or a version of one, down on the bottom right there. So that's showing, it's what process engineers use to work out how much energy in and out of a power plant. So we put a little bit of heating power in just to get our plasma going. That arrow's probably a bit big. It goes into the plasma region, and of course that's where the magic happens. That's the enormous energy that we get out from our plasma in the form of high kinetic energy neutrons. They crash into our blanket and we extract that thermal power. Only then we're going to at least need to make some electricity to run our power plant. We've got magnets to power, we've got coolant to pump, and all the other things you need in a power plant. And then, out of that, we need to make even more energy, because that is what you and I are going to switch our kettles on with when we've actually sold it to the grid. And so that conversion loss from thermal energy to electricity is very important. We know from thermodynamics it's hard to get that efficiency up. And the way you get it up is by running hot, making the hot coolant that goes into your turbines as hot as you can. And that's where the graph above comes in. And it starts to give you a little picture of the trace, the difficulty of engineering in the fusion regime. Because the red and blue line, they're a very standard fusion still. We love using them in the fusion industry. However, you go above 600 degrees with those, and what you can see is the yield stress, the strength of those materials drop. You just can't use them in a blanket when you're running very hot, that you need to get good electricity out, to get a good efficiency for your electricity generation. And so you start having to hunt around for other materials. You might have to do some advanced still that exists but needs development, or you might start looking for a completely different kind of material that you don't normally think of using. And that could lead you to somewhere like vanadium, which isn't a standard structural material, but could work for a blanket, particularly if it's working with pure liquid lithium. So these are the kind of trades we're having to make. This is the innovation that we are doing literally every day to make these things work. Let's talk about breeding tritium. So this is a picture of what Dennis described here. You've got your neutrons, they're crashing into your lithium and you're producing tritium, and you've got the equation down the bottom in case you're interested. However, the equation I'm really interested in is the one that says tritium breeding ratio is the tritium generated in the blanket divided by the tritium that you need to run the plasma. Quite simply, if your tritium breeding ratio is above 1, you do not need to buy any tritium. If your tritium breeding ratio is below 1, you are going to need to find some tritium from somewhere. So this tritium breeding ratio, we live and die by it in the blanket design business. So, what might this blanket look like? Well, this is a design that we showed at the Symposium of Fusion Energy Conference back in the summer. So it's a possible concept for STEP. You've got these big segments of blanket that you could lift out for maintenance, and those are separated into modules. And you can see you've got your first wall there, that's the survival region of your blanket. You then move into a breeding and heat generation area. So in this design, it's a kind of a bath of something perhaps like lithium in there, or maybe a pure liquid lithium or a lithium lead in there. And that is where the breeding is happening. And then that liquid could get taken off and put into the fuel cycle, the tritium extracted and poked back in. You've then got coolant pipes going through that blanket region. And that could have some different coolant in it, maybe carbon dioxide or helium. And that is getting the heat out and going off to the turbines. But this is just one possible design for a blanket. This is complicated, and this is supposed to be complicated, this slide, because you can make blankets at the moment in many different ways. You can have a different first wall material. You can have a different structural material. You could have a solid breeder, such as a lithium orthosilicate, that then you put a purge gas through to take away your tritium. We just don't know which are the right ones to go for at the moment, and which ones will be the magic ones that get out net power and the tritium we need. Which are going to be the best ones? And so, what we are doing, it's not just at UKAEA, all around the world, what companies and organisations are doing is we're unpicking this challenge. It means going to multi-physics, joined-up analysis code, where we have to start with the plasma equilibrium, which gives us our heat flux. That will tell us what our first wall needs to be made of and how fast we need to run that coolant, which in turn will tell us what the pressure inside that region is and how much structural material and what structural materials we could use. You then go into the breeder area and you start picking breeders and you start picking coolants, and you have to do the same thing. And you start to build up a geometry and a structure for your blanket. That structure is very important, because just think about it. Every time you put a structural material into a breeder, into a breeding blanket, you've got less room for breeder and a lower TBR. So you're trying to make these lovely, slender blanket designs, and yet they need to stand up to all that magnetic field force and that heat as well. So you're playing with this, and you run your neutronics analysis, and you get your tritium breeding out. So now you've got an optimization tool. You've got a thing you can circle around, and that is what allows us to start stepping towards the concepts we need to actually bring together the power plants that will produce tritium and produce net power. Once you've done all of that, you start looking at how many neutrons you've got left over. And you think to yourself, okay, I've got some magnets out the back there, I better shield it. And in the center column, that's a really tough challenge. You haven't actually got a breeding blanket for a spherical tokamak in there, so you've got a lot of shielding to do. You've got fast neutrons, you've got slower neutrons, and you've got gamma. But what you also have is really not a lot of space. And so you have to go for something really dense. Something like a tungsten is really where you need to be. But even better, if you put some boron or some carbon into that tungsten, it's even better, because then you can capture both the fast and the slower neutrons. And so this leads us to some of the things that we do in the fusion industry. We do things and say, well, tungsten pentaboride on paper looks really great. Shall we make some? And so we do. We go away and we work with universities and organisations to actually start making things like tungsten pentaboride that didn't exist before in real life. Now all we have to do is scale this up to something that's about 20 metres high and 3 metres diameter, but that is the job that we do. And that is just one part of the design that we have to grapple with. So I've kind of covered the green side of this, which is one part of sort of the trade area and all the decisions you have to make when you design a fusion power plant. I've talked about which blanket you use and what temperature the coolant should be. There's also decisions, just simple ones, like how many diverter regions are you going to have, or how big are you actually going to make your tokamak, and what power cycle are you going to use, and how are you going to maintain it, and how many ports do you need to maintain it? Would it be vertical? Do you need to take your magnets apart? These are all things that we have to do as fusion engineers, but it's also things that we literally are doing as fusion engineers. This is literally what I do every single day. I go to work and I design a fusion power plant that we are going to build at West Burton in Nottinghamshire. We are no longer in the time of fusion experiments. We are now in the time of fusion power plants, and this is what we do every day. So I hope you show you that it sounds like science fiction, but it's actually science fact. And not only that we are moving from experiments to power plants that actually can power our homes in a carbon-free way with abundant fuel. And I hope you find that as exciting as I do.